Hello guys and welcome to today's video. So I'm going to be showing us quickly an important reduction formula you need to know when solving problems in Laplace transforms. Now let's not forget that the definition of the Laplace transform of f of t is the integral, the infinite integral from 0 to infinity of the product of f of t and exponential minus st dt. So it becomes relevant to understand how to carry out special integrations when f of t is of the order t raised to the power of n, where n could be any number greater than or equal to 1. Okay, so when you have things like t square, t cube, t4, and so on and so forth. So how do you carry out something like that, especially when you want to find the Laplace transform? For instance, integral from 0 to infinity t dot exponential minus st dt, or you want to find the integral from 0 to infinity t square exponential minus st dt, and so on and so forth. So if you want to carry out integrals of this particular standard, it is important you know a reduction formula that will simplify the process and make you get your answers with minimal steps. Okay, so we are minimizing our steps and we are optimizing these solutions, or we are optimizing the time to actually obtain our solutions. So in the light of this, I'm going to be presenting to you a reduction formula. So follow me as we flow. So let's take, for instance, I want to integrate t raised to the power of n exponential at dt. So let me just use a for now. Okay, so let's say we want to carry out this integration. Permit me to skip the boundaries of the integral for now. If I want to carry out this integration, I can call the answer to this integral I of n. Okay, I of n, because the power of t here is n. So to carry out this integration, we will use our normal integral of u dv is equal to uv minus integral of what? V du. Is that okay? So you know the Lipet convention of carrying out integral. It is a convention that tells us how to prioritize the designation of a variable u. So all logarithmic function takes first precedence. All inverse functions like sine inverse, cos inverse, or tan inverse take second precedence. Then polynomials like x raised to the power of n or t raised to the power of n, and so on and so forth, take third precedence. And exponentials, then trigonometric. So this is the order of arrangement. Now, if you consider this integral, which one should we use as our u? Definitely, we are going to use t raised to the power of n. So u is equal to what? T raised to the power of n. So in this case, you're going to take this as dv. So this is u and this is dv according to this formula. So your dv is actually exponential at dt. So from these two equations, you could actually proceed and get the answer to this integral. So from the first equation, from the second equation, let me get what v is. So if you want to get v, you can integrate dv. So v is the integral of dv, which is the integral of exponential at dt. Now, when you're carrying this kind of integration, using integration by parts, you don't usually put the constant of integration yet till you're done with everything. So the integral of exponential at will be exponential at over a. Remember, okay? So this is the value of v. Now, my answer to the in, which is the integral of t raised to the power of n exponential at dt, will be my u, which is t raised to the power of n, according to what we said here. Then my v is going to be exponential at all over a, and minus integral of my v is exponential at all over a. So how do we get the u? Remember, u is equal to what? T raised to the power of n. So du dt is equal to nt to the n minus 1. The implication is that du is nt to the n minus 1, then dt. So du is nt to the n minus 1 dt. Okay, so just do normal differentiation. So at this point, you have that your in is equal to t to the n exponential at all over a and minus. If you factor out the constants, which are a and n, you have n over a. You can now rearrange the t to the n minus 1 first before the exponential at dt. So if you observe very closely, we can rewrite this as n is equal to in is equal to t to the n exponential at all over a, then minus n over a I n minus 1. Why am I writing the whole of this as in minus 1? Because we established that in is an integral where t has an order n in exponential at dt. So in is all integrals where t has a power of n. So in minus 1 will be all integrals where t has the power of n minus 1. In minus 2 will be all integrals where t has a power of n minus 2. In fact, I anything will be a integral where t has anything to as its power. Is that okay? So this is what you call your reduction formula. You are expected to memorize. Okay, so don't just memorize. We're going to learn how to use it. So how to apply it. So how to apply this reduction formula. So assuming you are solving a problem, let me just say I give you something like this to integrate. So I want you to integrate t square, then exponential let me say exponential 3t dt. I ask you to integrate something like this. So you can say let's I3 be equal let I2 be an integral such that the order of t is 2. Remember, these two numbers should match. So remember that you have set the stage. Okay, so from this point you can say using reduction formula, we have that in is an integral t to the n exponential at dt, which evaluates to t to the n exponential at over a, then minus n over a I n minus 1, just like we proved above here. Then what you can do is you can now start applying it gradually. Now you apply this reduction formula until you have I naught. That's where you stop applying it. Is that okay? And we are going to establish a special value for I naught for this kind of integral. Now I2 will now be, according to this formula, t squared exponential. In this place our a is 3, we have 3t all over 3, then we now have minus our n, remember, is 2 all over our a is 3, then we now have I 2 minus 1. 2 minus 1 is 1. Now you're not going to put your constant of integration till you have evaluated I naught. Okay, so at this point we are going to now apply the definite integral again. Sorry, not the definite integral. You apply the reduction formula at I1. Okay, so the aim is to apply the reduction formula till everything becomes I naught, and we'll now take it from there. So I2 will be t square exponential 3t over 3 minus 2 over 3. So our I1 will open a bracket, then we'll now follow this pattern, assuming n is 1. So we now have t raised to the power of 1 exponential. Our a in this case, remember, is 3. So we have 3t all over 3, and we now have minus a, n is 1 all over our a is 3, and we now have our I 1 minus 1 is I naught. So at this point everybody will be wondering what the value of I naught is. So don't fret. The concept is that our in was gotten from an integral t raised to the power of n exponential at dt. So I naught is t raised to the power of 0 exponential at dt, and t raised to the power of 0 is 1. So I naught is simply exponential, integral of exponential at dt. And I naught without the integration constant is simply exponential at over a. So anytime you're solving reduction formulas using this pattern, your I naught is just exponential at over a. So to wrap this problem up, my I2 becomes t squared e to the 3t over 3 minus 2 over 3. You now have your t to the 1 is t exponential 3t over 3 and minus 1 over 3, and I naught is going to be exponential. A is 3t, then you now have all over another 3. Is that okay? Then since you've evaluated I naught, you can now put your plus c. So your I2 is t square exponential 3t all over 3, then minus. Opening this bracket, you have 2 all over 9 t exponential 3t, and you now have plus 2 all over 27. You now have exponential 3t. Okay, how did I get 2 over 27? 3 times 3, 9 times 3, 27. Minus times minus plus, then you now have plus c. Is that okay? So this is how to apply an integral. Remember, I2 was the integral of t squared exponential 3t dt. Is that okay? So this method has shown us that with reduction formulas, we can get the same answer that we can use when we carry out the process using integration formula. That's addition rule. That's integral of u dv is equal to uv minus integral of v du. So reduction formula is actually a compression of this particular formula. With reduction formula, you usually bypass this phase of integration. All you just need to do is to apply the reduction formula like a recurrence relation until you get to I naught. Is that okay? Now let me show you a special case in Laplace transform. So assuming I want to find the Laplace transform of t exponential minus st between an interval. Let me say an interval. I can just label this interval 0 and 1, for instance, dt. So you just want to find something like this, a Laplace integral between 0 and 1. I call it a Laplace integral because of this Laplace variable s. So if you want to apply reduction formula to this method in solving this kind of problem, you can say let I, remember t has a power of 1 here, so I1 is equal to integral from 0 to 1. Then you now have t e to the minus st dt. And you now see using reduction formula, sorry, let me copy all this and paste it somewhere up here so that we can get more space. So using reduction formula, our in is given to us as the integral, okay, between some limits. Then we now have t to the n exponential at dt, which evaluates to what? Very good, tn exponential at over a minus n over a I n minus 1. So this is the recurrence relation or the reduction formula. So our I1 in this case will be following this pattern or following this formula over here. You have t raised to the power of 1, then exponential. Remember, what is your exponential? The a here is minus s. So anywhere we see a, we'll put minus s. So remember, this is a definite integral, but I'm not going to apply the definite integral till I finish solving I naught. Is that okay? So anywhere you see a, you replace it with minus s, t all over minus s for a, then minus n all over, instead of a you put minus s. Remember, a is minus s in this case, and you now have your I. Since n is 1, you have 1 minus 1, which is 0. And recall that I naught for this kind of integral is just exponential at over a, like we established previously. So I can replace this I naught. I1 is t1 exponential minus st over minus s minus n over minus s. Then instead of I naught exponential, remember a is minus s all over minus s. So now that I've replaced I naught, I can now apply the definite integral, which is from 0 to 1. Is that okay? Definite integral from 0 to 1. So you just have to simplify. You now have something like this. T exponential minus st over minus s, then minus s times minus s is minus n over s square, and you now have exponential minus st, okay, from 1 to 0. I hope I got that correctly. So we can now apply the definite integral. I is the integral from 0 to 1 exponential t exponential minus st dt, which is I1 is the integral, then which is definite integral when c is 1. So you now have 1 exponential minus s dot 1 all over minus s and minus n. Why am I still writing n here? Somebody should have corrected me. Oh, sorry. You're not actually here with me. So this is 1 and this is 1. Thank you for that. And this is 1. So why is it 1? Because n is 1. So let's not make that mistake like I did. So you have 1 over s squared dot exponential minus s dot 1. So anywhere you see t, you apply 1. After applying 1, you subtract. Then you now put 0. 0 dot exponential minus s dot 0 over minus s. Then minus 1 over s squared exponential minus s dot 0. Remember, this term is cancelling out to 0 because you have 0 times something. Then this term will become 1. Exponential minus s times 0 is exponential minus s. Exponential minus s times 0 is exponential 0, sorry. Exponential s dot 0 is exponential 0, which eventually becomes 1. So anytime you encounter something like this, just know that it evaluates to 1 unity. Okay, so let's apply and get our answer. I1 is integral from 0 to 1 t exponential minus st dt, which is 1 times this will give you minus exponential minus s all over s. This minus sign has come up here, then you now have minus. If you simplify this, you get exponential minus s over s squared. Then remember there is a minus sign here, and you now have this one is 0, then minus. Remember the denominator becomes the numerator becomes 1, so you just have 1 all over s squared. Okay, so when we write it, we'll have minus exponential minus s over s minus exponential minus s over s squared, and minus minus is plus 1 over s squared. So at the end of the day, this is what you have with reduction formula, the integral from 0 to 1 t exponential minus st dt. Put the plus before the minus, you get 1 over s squared and minus exponential minus s over s minus exponential minus s over s squared. If you simplify a little bit further by factoring out 1 over s squared, you get 1 over s squared into, this middle term. You can modify this middle term. If you multiply s here, then this one will become s squared. Is that okay? So this is how it was before. There was no s, but if you put s here, then you have to put s in the denominator, making it to be s squared. So if you factor out 1 over s squared, you get 1 from this term, and you get minus s exponential minus s, and you get minus exponential minus s. So finally, to wrap up your answer, integral from 0 to 1 t e to the minus st dt will evaluate to 1 over s squared into 1 minus, factoring out e to the minus s, you get s plus 1. Okay, so this is it. With reduction formula, we have achieved this particular answer, just as we would and with any other method. But why I like the reduction formula method is that if you know it, it's something that you might frequently encounter for this kind of purposes, and you can easily apply this method to solving problems of this order. So whenever you see a problem like this, don't be afraid to use reduction formula. The summary is that whenever we are given any in of this form, integral of t to the n exponential at dt, where a could be anything, any number, then your answer is t raised to the power of n exponential at over a, and minus n over a, then in minus 1, where in minus 1 will be the repetition of this whole stuff, where you just replace n with n minus 1. Is that okay? And we also established that for this kind of question, I naught is just simply exponential at all over a. So take note of these two properties of reduction formula. So these are two properties of reduction formula that you should know for this pattern of integration. If you know this, it will help you to simplify problems of this order, especially for the ramp or sawtooth function, where our f of t is equal to t. So the sawtooth function was what we solved here, okay, in this case. So for sawtooth function or ramp function, this is like a bigger version of the sawtooth. The ramp function stretches to infinity, but the sawtooth is just a portion like this. Sometimes it may keep repeating and so on and so forth. But the ramp function just stretches, and the ramp function is a function such that if you give it an input A, it returns A. If you give it B, it returns B. So if here is 1, here will be 1. If here is 2, here will be 2. If here is 3, here will be 3. So that's why the property of this function is your y and your t. Your y is equal to t, or your y of t is equal to t. So y of 1 is 1, y of 2 is 2, y of 3 is 3, and so on and so forth. So that's why you have it like this. So it's a ramp function, or it's the same as your sawtooth function. That's when you just have sections of the function like this. Um, Enough about that. We'll see more about sawtooth function and different functions in upcoming videos. So be sure to subscribe to this channel and be sure to check the Engineering Mathematics playlist so that you will get all the videos on Laplace transform applications, or Laplace transform to finite time domain signals, or finite time domain graphs. So thank you for watching. I hope you've learned something meaningful today. Don't forget to like and subscribe to my channel. Your likes means a lot, and your subscription means a lot, and your sharing too also means a lot. So I'll see you in the next video. Bye. Stay blessed.